What's up, guys? So in this video I want to talk a little bit about end behavior of polynomials and some other characteristics of polynomials. And to do this, I've already got some pretty good notes on it. So I'm just going to kind of narrate these notes. I know some people prefer videos to the notes and some people can't view the slides very well. So I'm just going to go through and kind of add a little bit to each one of these slides. At any point, you may want to pause the video and take notes if this is how you're getting the notes. And I'm just going to talk a little bit about each one of them. So first of all, vocabulary here, these are the things that you're going to make sure you need to know for this unit. The degree is the highest exponent of x in the polynomial. The leading coefficient is the coefficient of that term. Whichever term had the highest degree, the highest exponent, the leading coefficient is the coefficient of that term. Make sure you notice that does not mean it does not have to be the first term. The terms could be out of order if it's not in standard form. We'll see that in a minute. And then turning points. A turning point is where the graph changes from increasing to decreasing. So like at the top of a roller coaster, it goes up and then comes down, or if it hits the bottom and then comes back up, that's a turning point. And the number of turning points is always going to be equal to the degree minus 1, the maximum number of turning points. Now you may have no turning points, but you will always have at most whatever the degree is minus 1. And then the real roots. The real roots is values of x for which y is 0. So the real roots are numbers that you can plug in for x that make the whole thing equal 0. It's the real roots are the roots that have to be real numbers. There's also imaginary roots, which we'll talk about later. Zeros and x-intercepts are the same thing as roots. So if I say the zeros of a function or the x-intercepts of a function, those are the real roots. You plug something in, you get out a 0. That's what an x-intercept is. It's where y equals 0. Okay, so here's an example. In this first example, the leading coefficient is 7 because the highest exponent is the 3, which makes this term the term we look at for the leading coefficient, which is 7. In the next example, the degree is 5 because the highest exponent is 5, which means the leading coefficient is 3. So you need to note here that the leading coefficient is not the first coefficient in this case. Now, that's because this is not written in standard form. Standard form would have it in decreasing order. And since it's not in standard form, you got to look somewhere else for the leading coefficient. End behavior. There's a lot to be said about end behavior, but in general, I like to think about it this way. If something has a degree of 1. If you have a degree 1 function, that means it's linear. That means it's like, y equals x plus 2, just a linear equation. If it's positive, it's going to go up to the right and it's going to go down to the left. Okay? Positive meaning if the leading coefficient is positive. If it's negative, it's going to go down to the right. Uphill, downhill. Okay? Up to the right, down to the left. Negative, it'll go down to the right and up to the left. If we look at an even degree, that's a quadratic. We know quadratics either make a U if they go up, or if they're negative, they go down. If they are positive, they go up to the left and they go up to the right. Negative functions go down to the left and down to the right. Third degree would be cubic, and they don't always have this little curve in the middle. Sometimes it just kind of hits a point and then turns up without actually turning all the way down. But I like to show the maximum amount of bendiness. This is the most bendiness that a degree 3 polynomial can have. It can have 2 turning points. Notice it turns at the top here, and then it turns again here. Going back to what I said before, that's 1 less turning point than the degree. 2 turning points, degree 3. This had 1 turning point, and it's degree 2. So if it's positive, it's going to go up to the right, down to the left. If it's negative, it's going to go down to the right and up to the left. Degree 4 goes up both ways, or it goes down both ways. And again, 1, 2, 3 turning points. It's 1 less than a degree. Now, what I'm talking about over here is that you should notice a pattern with the odd degrees going up to the right and down to the left if they're positive. See, this goes up to the right, down to the left, same as this. And if they're negative, down to the right, up to the left. And the even degree functions go the same. Either if they're positive, they both go up, or if they're negative, they both go down. Same thing on the fourth degree. Anything that's even is going to follow the same pattern. So what this means is when you're trying to figure out end behavior, all you got to do is look at whether or not the degree is odd or even, because this pattern is going to continue. Every time the degree goes up by 1, you add another turning point in. So if this was the next one would be degree 5, just imagine bending one of these down. Well, now the ends are going to go in opposite directions. Okay, so how can we make this easier? All we got to think about is the degree being odd or even, not exactly what it is. If it's odd, it's going to act like a line. It's going to act like a degree 1 polynomial. So if the degree is odd, it's going to go up to the right and down to the left if it's positive, down to the right and up to the left if it's negative. It may do some squiggly stuff in between, depending on what the degree is, but it's going to go down to the right, up to the left if it's negative, up to the right, down to the left if it's positive. Same thing with even degrees. Even degree function is going to act like a quadratic in terms of the end behavior. It may do some stuff in the middle, but it's either going to go up both ways or it's going to go down both ways. Okay, so the notation that we use when we're talking about this, we don't just say to the right or to the left or up or down. Of course, it's math, so we got to make it more complicated. So we say to the right, we say as x approaches infinity, and we use this symbol. So what's in bold is what you're going to say. As x approaches infinity, the arrow means approaches. Remember that the x and y axis, if you've got an x and y axis, x increases to the right and decreases to the left, where it approaches infinity as you go to the right, it approaches negative infinity as you go to the left. Y, or f of x, approaches infinity as you go up and approaches negative infinity as you go down. Okay, so as x approaches infinity literally just means as you go to the right. As x approaches negative infinity literally means as you go to the left. F of x approaches infinity means goes up. F of x approaches negative infinity means goes down. So if you say, for example, as x approaches infinity, f of x approaches infinity, you're saying as you go to the right, go up, or the graph goes up. We'll look at an example. So here's this, looks like a fourth degree, which means it's even. And so it's going to act like a negative quadratic. And so even though it's not actually going to look like this, the end behavior is going to act like this. It is going to go down in both directions. Now again, it may do some squiggly things in the middle. It may go down and back up and then back down again. Maybe it will, maybe it won't, but it's going to go down in both directions regardless of what happens in the middle. So for the purposes of end behavior, I like to do a little sketch to remind myself what's going to happen. It's even, so it's a quadratic, or like a quadratic, and it's negative, which means it'll go down both ways. Okay, so to the right it goes down, and to the left it goes down. So as x approaches infinity, as you go right, f of x approaches negative infinity. The graph goes down. As you go right, the graph goes down. As x approaches negative infinity, as you go to the left, f of x approaches negative infinity. You go down. Here's another example. X is to the third power, meaning it's odd. So it's a third degree polynomial, which means it'll act like a line. And since it's positive out front, the leading coefficient's positive, it's going to go up to the right and down to the left. So again, up to the right, down to the left. As x approaches infinity, as we go to the right, f of x approaches infinity. The graph goes up. As x approaches negative infinity, as you go to the left, f of x approaches negative infinity. You go down.